Hello, you're currently watching the Design Explorer webinar and how it is that we can set up an analysis of a model that we already have through a design of experiments. So you might recognize this truck model that we already have on the screen. Now what we're going to do is isolate into an area of focus, and what I'd like to do is focus upon this lower and upper cross member on the chassis of the vehicle. Now, just to maintain this sort of focus, you'll know that if I click on this camera icon, I can click on the set of parts and you can see that I want to focus on this set of components only. Now, to get started, what I'm going to do is bring up a model whereby I already have all of my morphing constraints and morph shapes applied to this. So if I can show you what I already have, so in a different isolated study, you can see that I've got two load cases set up for this set of components. We have the vertical deflection, so you can see it's held using SPCs on these edges, and there is a vertical force acting on my cross member, and there's also a horizontal force acting on my cross member as well. And to show you my morphing shapes I have applied to this set of components here, I've got three different ones. I've got the rear mount morph, so you can see it changes the shape of this mounting plate. I've got the same one but on the other plate as well. And last but not least, I also want to thicken up this whole part itself. Okay, so these are the three morph shapes I'd like to carry through to my design of exploration. I also have different property thicknesses for the different parts. So if I can show you what the thicknesses look like, you can see the upper and the lower cross member parts have the same property cards, and so do my two plates. And in terms of thicknesses, this is what they currently look like. So we've got 2 mil thick bars and 2.6 mil thick plates. And from a baseline analysis that I've already done, you can see that from those two load cases, this is the displacement that it's undergoing. And very quickly in the post-processing, if you click on contour and you click for stress, then you can see how you can look at the different results of your components. Okay, and then to change the subcases at the side, you can change it from the vertical deflection to the horizontal deflection as well. And to change the deformation scale of it, we can click on deformation and increase this to 100 just to make it look a bit more obvious graphically. So in order to launch up the Design Explorer on our model, all you need to do is in the top ribbons where you see Design Explorer, there will be a compass because we want to explore the design that we're looking at. So if you were to click on that compass, you'll see the Design Explorer browser pops up on the left hand side, and with this multifunction icon button, you'll see there is a plus button in the top left corner. If I were to click create, then this is where I can create my new study. So I can click on create exploration. For now we'll just create a design of experiments. We can specify the location of where it is that I want to save my folders to. So if I were to just copy and paste this location, then it'll save it in there. But to further refine it as well, I can create a study. So if I were to click on new folder, this can say my DOE, and I'll know that all of my results will be stored in that folder there. The only slight discrepancy that you need to make sure the location is to have enough hard disk space to keep all of your results that you'll get out of this design of experiments. I can also rename it as well, so I can call this my cross member DOV. Click enter and you'll see that it's saved. Okay. So as we go through, you can see we work from a left to right vertical. So if I were to just select these ribbons being my tools, and you'll see that we work from left to right. So we started our creation off using the compass. I will then click for gauge. So with gauge you can specify what of the input parameters it is that you're willing to vary within your design. So if I were to select this property as well, and this one, and my lower plate, then these are the 3 different property cards that I'm willing to change the thicknesses of. So I can increase them by 50%, decrease them by 50% as well, and click create. You'll see this very quickly generates the thicknesses that we're willing to vary. Same with the shapes. If I click on shape, I can then select which shapes they are that I want to reinforce onto my design changes. I can click OK, and you'll see it's generated another 3 different design variables. Now to actually visualize these, I can go back to looking at what it is that I'm varying in my model. So you'll see I have 4 different components, and if you hover over to any one of these review buttons, and within details you can see exactly what its current nominal values are. So nominal values are the thicknesses that your components are currently residing at. So if I were to click on preview, you'll see it isolates what part we're looking at, and you can see the hypothetical thickness that's going through that property. So if I were to increase it to the maximum, then you can see it gets thicker because that's 3 mil, and if I make it thinner, then that's 1 mil. Okay. You can always increase the values manually, so you can overwrite the percentages you had put in. So I can make this 6 mil instead, and I can make it as thin as 0.5 mil. You can feel free to adjust these as you see fit. And of course, when it comes to looking at the morph shapes that we have, you should think of the 1, -1 and 0 as a scale factor. So if I were to preview, let's say this one plate here, pushing it to the maximum will move it to the utmost extremity of that morph shape you implemented onto it. And if you go to -1, then it does the inverse of that design change you had. So what I could do is always limit the amount that it can move by, so I don't actually want it to reduce my plate sizing. I can specify that the minimum that it can move to is half of that minus scale factor, and I'll limit this for both sides, and I can leave everything else as default. But this is the preview buttons that you can use to understand what it is that you're changing in your model. After we've defined all of our input variables, so the things that we are willing to change in our design itself, we now need to specify what our responses will be. Now usually these responses are the outputs which you want to look at after you conduct an analysis. So for this instance, I'm going to specify displacements as well as stresses, because these would be my key performance indicators in how well my design is doing. So if I were to click on displacement, you can see I can specify that node there. You then select a load step that you want to measure this displacement from. So let's say it's for the vertical deflection, and I'll give it a tick. You can see this double chevron area also tells us which component we can specify for and what request type as well. And once you're happy with that, I can click OK. Should you wish to change any of it again after you've created it, you can do so in the entity editor. I could select displacement again, and let's say if I were to select displacement on that node there, I can then select which node step I want it for, and we can do it for the horizontal deflection load case. And same again. So I can rename this to being my vertical displacement, and this one could be my horizontal displacement, just so I know which displacement reflects which load case. Okay. Now after we've done this, I can also go back and click on stress/strain. So with this measure, you can either check for the maximum stress across a whole property, or better yet, you could specify a specific element which you want to record the stresses from. So I could select that element there. Same again, I would then specify the correct load case, so I'd select vertical, ticket, and click apply. This then sets me up in a good position to then check for the stress on this element, and I apply this to the horizontal load case. And then once I'm okay with it, if I click on the green tick, then it would execute the task as well as coming out of the tool. Again, I can click on the stresses on the side and you can see in the entity editor what it is that I'm requesting for, and you can see which element it's selecting on. There are also a few other options that we can go through. So later on, when we want to look at an optimization, that's where we can involve looking at the mass or the volume of the overall assembly. We can also look at the reaction forces at single point constraints. We can look at the frequency of a model. We can look at connectors, the measurements. So if we're looking at the relative displacement or the contour plot of a certain response value, then we can click for measure as well. And you can also derive your own responses. So it could be the sum of certain responses you've requested for already, or it could be the average. You would construct it like you would with an equation. So once we're done with all of these responses, we can then click on evaluate. So with this play button here, we're just conducting a design of experiments to begin with, so we can address the objectives and constraints slightly later. We can specify the DOE type that you want to look at, so you can look at a full factorial, MELS, which is the modified extensible lattice structure, and then we also have the Latin hypercube. So we'll keep it to MELS because that is a nice space filling algorithm. It will then, because of this algorithm type, there is a recommended number of runs for it to run based off of how many input variables you have and the amount of responses you have coming out of it. It would suggest a good number of runs to give you an accurate sort of understanding of the relationship between the input parameters you have and the output parameters that you've requested out of it as well. So it gives you a really good understanding of how it is that your design inputs affect the overall result at the end of it. We can look at multi-execution, so I can ask for it to run 5 jobs in one time, in one go. I would specify my OptiStruct solver, the solver argument, so if I want to dedicate 6 cores towards it. And once I'm happy with all of this, so let's say if I kept to the default values, click export where it generates all of the decks for you, but you can always just click run, as this does the same thing. And you can see now it brings up this table and you can see this task that's at hand. So as you can see, I just clicked run, and now I wanted to show you an update on the status of what it looks like. So you can see the status between my nominal run and all of the different variations. It gives you a status as to if it's pending, processing, or completed. One of the coolest things about this as well is the fact that whilst this is solving, for any of the legacy HyperStudy users amongst us, HyperStudy is still in its same format, but the Design Explorer tool is basically a mini HyperStudy built inside of HyperWorks. And we can see that specified directory that we had here. It creates all of these HyperStudy archives for us. You can see a session file, it's got the model file that we're using, and throughout the approaches you can see the whole folder structure. So you can see the runs that it's doing for this DOV, and within model 1 you can see it's generated that model for us, and it's also got the results there too. So this is one of the wonderful things, in that should you wish to look at the files outside of this solve, you can. So now that my runs have finished running, you can see in the status bar, if I expand this box, you can see all of the 31 runs that I've done, And if something is complete, then it would be in green. If you do see a failed run, then that would show up as red. It's not a big issue if this does show up as failed. At times, say if there are some conflicting morphing scale factors, then this could cause a failure. Purely just maybe could be element quality that errored out. I wouldn't worry too much about it because you've still got all these other 30 runs and the data behind it to understand that relationship between your deck. However, just beware, if you do start your run off and it starts at failed already for everything, then that's when you might need to head into the folders, look at the run itself. So the way in which you would diagnose it is I can go back to my DOV, click on run 31, and as you normally would look at the out file, you can look at the out file in this one to see what the error is. So once this is all ran, if you want to click on this icon here, so the 3 I-beams, this then brings up the Results Explorer. So this is a really powerful tool to help you understand the data that you have behind all of these 30 runs. So you can see all of your different input parameters are listed here, and then your output parameters are also in these columns at the back. So you can see just how if you were to vary the thicknesses from 2 to 3.8 to 0.72, then this obviously shows you what results it got out of it at the end. And you can always filter them down. So let's say if we didn't want to look at all of the inputs, I just wanted to look at my upper and lower thicknesses against the let's say stresses, so we can see whether if there is any sort of correlation between the two, then you can always tick for it this way. But for now, I'll just make sure I have everything left on activated, so we can see everything here. Now, if you were to look at an ideal run that you wanted, so let's organize all of this by the lowest stress or the lowest stresses, then we can always click on each of these to see which one's lower. And if you were to right click on it, you can then compare it with the nominal run. So what this means is it's going to take run number 19, where it gives you the lower stresses, and you can see just what changes in the input parameters has been made in order to give you those results. So here you can see the actual delta change between the designs, and you can see if it's a positive or negative change as well. So after we've looked at all of that, you also have the linear effects tab, whereby you can specify which output response is you want to look at. So let's look at vertical displacement for now, and you can see whether if those different input parameters have a positive or negative correlation towards those responses. So we can see this rear mount. So with this rear mount itself, the morphing change, if we go into that morph, there's a positive correlation between the displacement increasing. And let's say if we were to look at the thickness of this plate, the thicker it is, the lower your displacement value is, hence there is a negative correlation. And that makes sense. We can also look at stresses, and as we can see it, there are some thicknesses that are positively correlated, so we need to be careful about those design changes. But there are other thicknesses whereby the thicker it is, the lower the stresses. And this does work out very nicely because the thicker this part is, the lower the stresses, which is understandable. So all of this is just a nice understanding as to which inputs really do affect those key performance indicators you care about, and where we're looking at a trade-off at the end of it. So with this example, what you would want is an R-squared value being as close to 1 as possible, as the closer it is to 1, the more accurate the surface fit of the data you have in the background against the real data actually is. So for instance, if I'm going to move all of these different values at values that we haven't solved for, this will do a nice sort of extrapolation. So this whole design study here, it will then generate what the outputs would be based off of that surface fit that we had on the solved data. But, however, because these R-squared values aren't the most accurate, as in they're not the closest to 1 as they could be, to improve this value, what we could do is conduct more runs in our MELS DOV. So in the initial slide where it asked for how many runs you could do, you could have increased that number. Or better yet, if you did have them set here, you can always verify it and it would resolve your model with these input values in to get you the real result. And this last plot here is just a scatter plot. If you wanted to look at a hypergraph version of the scatters of any positive or negative correlation between your input to output data, then that's where you can plot it on. But what I also wanted to show you from this results browser, last but not least, is let's say if we were to head back into the lowest stress again, we can look at, it was run number 19, I believe. Let's order this by this one. Here we go. Or run number. Sorry, it must have been the displacements that I mentioned. So, displacements. Well, let's look at this one. It's run number 25. That's the lowest currently. And we can always look for that one. So, if I were to right click on that one, I can also load the results immediately. So if I were to click on load results, it's already synchronized in terms of the view between my model and my post-processing window. And you can see these have near to being fully morphed plates. There's no sort of horizontal thickening. There might have been a small reduction, so instead of it being thicker, it's made it thinner. And you can see that it's increased the displacement up into nearly 2 millimeters. Okay, so this is a really nice way in which you can load your results and see exactly what that model would look like compared to your nominal model. Okay, so after we've conducted that DOV, we can see, we've got a multitude of results that we can look at, and we now understand the relationships between the design changes we want to make and how it affects our results. Should you wish to conduct more analysis on this, then you can always look at the HyperStudy archive you have, and you can open this in HyperStudy itself. And if I were to do this, then you can see the structure and the layout behind it. So where you have your original model, the nominal model, you can then see the DOV that we applied onto it. So how it's using that modified extensible lattice sequence, the MELS algorithm, and then we can look at all of the data behind it. So you can look at the evaluation data, and this is everything that we saw in HyperWorks already. And it's that final post-processing report where it tells you, if there were any bad values, then we can exclude them. And lastly, it also looks at the HyperStudy side as well. So with the fit, that is applied that surface fit to it, and you can see what algorithm it used to understand it. So last but not least, what we can also look at is if we took this DOV that we had and we wanted to turn it into an optimization. It's very simply done. Just click on that plus sign again, and instead of creating a DOV, I can click on the plus sign and click for optimization. I'll save it in the same directory as I did last time, and I can just simply close it. Look at my Design Explorer tab. You'll see that this has been now enabled, and what I could just do is select everything that applies for this optimization, which is all of the ones that I had for my DOV. So when you're conducting an optimization, we also need to look at instructing an objective as well as a constraint. So let's create one new extra response. So I can look at the mass, or maybe the volume, so the total volume of everything, and that will be one of my responses. There we go. So I have volume 1, and I'll just keep it as that. I can then also specify my objective, so I can specify a response, and I can tell it to go by volume, and that I want it to minimize the amount of volume But then my constraints can be that I don't want my vertical displacement to be greater than 1 mil. And you can also add in a few other constraints, such as stress values can't be over a certain amount either. So let's say I go with my horizontal displacement stress, so my horizontal load case stress. I don't want that to be greater than 500 megapascals. So now it needs to give me a very specific design which meets this set of criteria here. And if I'm happy with that, I can click play. And this time it's an optimization, so it'll give you a recommended number of run of 50, and that's the amount of iterations it go through to find you that perfect result. If it finds that perfect result at iteration 18, then 18 would be the ideal run to go with. Multi-execution will keep it as 1, and you still use 6 cores to run with. And after you click run, you can see the exact same screen, and I will show you what happens once they've all finished running. Okay, so once you can see it's finished optimizing, say if you were to right click on them, not only can you load the results to understand what the outputs are, if you were to click browse results, then same again, it will show you the folder directory and where you can look at it. But first things first, we can actually close this off and look at the optimization results. And you can see from here it's got all of the different runs that it's run at, and there is a color coding, so out of all of the runs it did, it has shown that this is the optimal design to get what it is that we wanted. So where it's got the most minimum volume, it also ensures that our displacement is less than 1 mil, like we had instructed for it to be. Okay, so if I were to just right click on this, I can load my results, it will bring this up, and from here we can see exactly what this design looks like. So if I were to zoom in to this plot, then we can see it's fairly similar to what we already have now, just a few small tweaks to the thicknesses, and ultimately, same again, you got the evaluation plot, iteration plot, and scatter plots that you can look at as well. So I can right click, compare that with my nominal run, and we can see how much of a design change there has been. But ultimately I can click on another run, let's say with this one, I can compare that one to my optimal run. And that is the Design Explorer tool. Thank you very much for listening.